Good morning, friends, and I warmly welcome to all of you in the series of Mechanics of Solids. Today, we are discussing a new chapter on shearing stress on beams. Prior to start about the shearing stress on beams, let us discuss what we have studied up till now in the series of Mechanics of Solids. Come to the PPT. We learnt in the previous session about types of supports, loads and types of beams, support reactions of statically determinate beam, shear force and bending moment diagrams of statically determinate beam, bending stress distribution diagram at a section on the beam. Today's objective of this session is define the shear stress, derive the shear stress equation at a section, if possible draw the shear stress distribution for the rectangular, circular, IT sections and some other sections. Introduction. We have seen in the previous session about bending stress in beams. We have seen that a part of a beam is subjected to a constant bending moment and zero shear force. There will be only bending stress in the beam. The shear stress will be zero as shear force is zero. But in actual practice, in actual structure, beam is subjected to a bending moment which changes from section to section. Also, the shear force on the beam is not a zero. It also varies from section to section. It is important to note that a beam always the shear force changes from section to section along with the bending moment. So we cannot avoid the word shear force. So due to this shear forces, the beam subjected to the shear stresses. These shear stresses will be acting across transverse sections of the beam. These transverse shear stresses will produce a complementary horizontal shear stresses which will be acting longitudinal layers of the beam. Hence, beam will also be subjected to the shear stresses. Now, let us be understood and let us be derive the equation for shear stress right now. So, now let us come to this particular tabletop that what we want to understood by shear stress. Now, here say a beam is there with any kind of loading. So, any kind of beam with any kind of loading, when we have plotted the SFBM diagram, it will be visualized that shear force changes from section to section, bending moment changes from section to section. So here we have across the point where shear force changes a sign. At all other points there will be a certain value of shear force, and this shear force leads shear stress. And our intention is to find out the equation, the variation of the equation of the shear stress. Now look to this PPT, the figure. Figure first one, this A figure shows a simply supported beam with UDL. Now, from a UDL, the shear force and bending moment will vary along the length of the beam, and we know how to plot. Now, to visualize the detailed depth, let us take two sections AB and CD of this beam at distance dx apart. Between those two sections, clearly visualize the figure B. section AB, section CD, and the distance between these two sections is dx. Now, let at the section AB, F is the shear force and M is the bending moment. If you want to visualize, clearly visualized over here. Now, let us be understood by over here what the statement has been told. A beam with UDL, I want to two sections, and I want to visualize. I will enlarge this figure. Then this total available beam depth is like this. This is one section, this is another section, named called AB, named called CD. Now, if I want to plot the diagram of shear force, the shear force diagram is like this, and this will be your bending moment diagram. So what the statement has been told, that this is the shear force F which is acting at section AB, and this will be the bending moment M which is acting on section AB. Similarly, on section CD, the shear force is F plus delta F, and bending moment is M plus delta M. This is the words to be used over here on this particular PPT. See the PPT. F plus delta F, that is the shear force which is acting on section CD, while M plus dm, that is the bending moment which is acting on the section CD. I, that is moment of inertia of the section above the neutral axis. Now, it is required to found the shear stress on the section AB at distance y1 from the neutral axis. I will repeat the statement once again. Our intention in this particular equation is to find out what is the value of shear stress at distance y from the neutral axis. Let's see the figure on this tabletop. This is my neutral axis. This is one section I am interested to take, this section which is available at depth y. My intention is to find out the variation of shear stress on these layer. If you want to visualize the clear figure, please visualize the figure over here. This is the layer at distance y1 from the neutral axis. I want to find out what will be the value of shear stress variation on this layer. Visualize clearly. F, shear force acting on AB, M, that is the bending moment acting on AB, F plus dF, that is the shear force on the section CD, while M plus dm, that is the bending moment which is acting on section CD. Now, let us visualize the figure C, which is detailed, show the cross section of the beam. On the cross section of the beam, let EF be the line at a distance y1 from the neutral axis. Now, this is a 3D figure of a beam. If you want to visualize very clearly this 3D view of a beam, you can visualize that this is my neutral axis which is passes from the centroid of a figure, and EF, that is the line which is available at distance y1 from the neutral axis. Now, consider the part of the beam above the level EF and between the two sections AB and CD. What the words has been stated, that consider this full area, consider this full available area between this section. This is the first section, this is the another sections, and the available area with you is this one. This part of the beam may be taken to consider of an infinite number of an elemental cylinders which is on this area availability. So, refer the figure clearly. This one we have to consider the element cylinders each of the area dA and length dx. So this is the elemental small cylinder which is having an area dA and the length is dx. All the three figures which has been drawn simultaneously, original figure of a beam shown the two cross section. Here the two cross sections which is shown from the elevation point of view AB and CD, and this is another figure C which is shows section AB, section CD, available distance dx. We are considering the area above this level EF, in which the one cylinder we have considered of the cross sectional area dA and the length dx. So consider one such element cylinder at a distance y from the neutral axis dA. Remember this word, y from the neutral axis. If you want to refer a figure, this y1 is the distance available for the layer EF, but y distance which is available of a particular cylinder, I will repeat the one word, y1 and y both are the different things. Y1 is the distance for a layer EF, while this y is the distance from neutral axis to the one particular selected cylinder. dA is the area of elemental cylinder, dx is the length of elemental cylinder, y is the distance of elemental cylinder from the neutral axis. Let sigma, that is the stress, that is the shear stress intensity, the word, it is not the shear, it is the bending stress, intensity of bending stress on the end of the cylinder of the section AB, while M, that is the F plus sigma F, that is here the word or nomenclature has been used as sigma plus delta sigma, that is the stresses, bending stresses on the cylinder on the section CD. Now the bending stress at distance y from the neutral axis is given by m over I is equal to F over y. F, we are using the word sigma, m over I is equal to sigma over y, that is sigma is equal to m over I into y. That is the basic equation that we have already been studied in the case of the chapter of bending stress. Now for a given beam, the bending stress is a function of bending moment. Sigma is directly proportional to the m, and the distance of y from the neutral axis means sigma is also proportional to the y. So let us find the bending stress on the end of the elemental cylinder at the section AB and the section CD. Then the bending stress on the end of the elemental cylinder of the section AB, where bending moment is m, is equal to sigma is equal to m over I into y. While this bending stress on the end of the elemental cylinder on the section CD, where bending moment is the m plus delta, that is dm, that will be equal to sigma plus delta sigma d sigma is equal to m plus dm divided by I into y. Now let us find the forces on the two ends of the elemental cylinder. Force on the end of the elemental cylinder on the section is nothing but the stress multiplied by cross sectional area of the cylinder. Stress on the section AB is already known to us, that is sigma. Area on the elemental cylinder we know, that is dA. We know the formula of sigma, that is m over I into y multiplied by dA, that is the force on the end of the elemental cylinder on the section AB. While the force on the end of the elemental cylinder on the section CD, that is the stress multiplied by area, that is the sigma plus d sigma into dA. And if you put the value of sigma plus d sigma, that is nothing but m plus dm divided by I into y into dA. So these two values are nothing but the forces at the end of the elemental cylinder. So if you want to visualize that particular figure clearly, just visualize this figure. The force which will be developed over here that is m over I into y into dA, while over here the force will be developed is m plus dm divided by I into y multiply by dA. Now let us find this forces that is already known to us. Now at the two ends of the elemental cylinder the forces are different. They are acting along the same line but are in the opposite direction. Hence there will be unbalanced forces on the elemental cylinder. So net unbalanced force on the elemental cylinder, which we can obtain by subtractions of the two value, that is m plus dm by I into y into dA minus m by I into y into dA. And if you want to simplify this, I achieve an equation that is the net unbalanced force on the elemental cylinder is equal to dm by I into y into dA. That is our equation number 1. The total unbalanced force above the level EF and between the two sections AB and CD may be found out by considering all the elemental cylinders between the sections AB and CD and the level EF, and that is achieving by integrating the equation number 1. Equation number 1 which stated that net unbalanced force that we achieve as if the net unbalanced force we achieve, that is dm by I into y into dA, that is available for one particular layer, one particular section. Now that we have to integrate to obtain for a whole section. So if you want to visualize, this is the net unbalanced force on the elemental cylinder, that is this one dm by I into y into dA, and to obtain the full, that is the total unbalanced force that we can achieve by integrating this equation, that is the total unbalanced force that is equal to integration of dm by I into y into dA, and that is achieved